Hello, this is going to be the lecture over chapter 17. This is going to be the second part of waves. All right, so sound waves are longitudinal mechanical waves that can travel through solids, liquids, or gases. You can see here in the diagram there that point S is going to represent a tiny sound source that's going to be referred to as a point source. That's going to emit sound waves in all directions isotropically. A sound wave is going to travel from point source S through some sort of three-dimensional medium. The wave fronts are going to be those little circles that you see, and they're going to be the surfaces in which the oscillations due to the sound wave have the same value, basically the same phase. And these wave fronts form spheres centered on S, assuming that you have a uniform density and things of that sort in the medium. The rays are radial to S. In other words, they're going to stick out at a certain distance, like having a circle and a radius drawn to the center of the circle. And so the short double-headed arrow indicates that elements of the medium oscillate parallel to the rays. So they're going to work pretty much in the same dimension. So the speed of a sound wave in a medium having a bulk modulus B and density rho is going to be equal to the square root. You're going to have the velocity is equal to the square root of the bulk modulus divided by the density. This is going to be the speed of sound. So you can see here that we have a tube, and we can see a pulse that's exists right here. It has an increase in the pressure, P plus delta P, and I guess I can blow this up to actually be able to look at it. Not all idea. So we've got P plus delta P, and then we've got the velocity plus the change in velocity. We have a moving air piece here, moving at a particular velocity. It's covering a certain distance. So an element of air that has this width is going to move towards the pulse with a particular speed v. So through Newton's application of to direct application of Newton's second law, we can come up with this. So the leading face of the element enters the pulse, and the forces acting on the leading and trailing faces are shown. So you can see pressure times area right here, and then you can see the pressure and the little bit additional to that times the area over here. So you can see that change there. Okay. So a sound wave traveling through a long air-filled tube with speed v consists of a moving periodic pattern of expressions and compressions of the air. The wave is shown as an arbitrary constant. So let's kind of blow this up and see what we're talking about here. So you've got the compressions, you've got the expansion, and this pulse is repeated all the way through. And you can even see the wavelength, the distance in between the common point in the waves is marked out here with lambda. And you can see here that the sound wave is traveling through here with speed v. And so the element oscillates left and right as the wave moves through it. So these elements are moving this way and then that way. That's characteristic of a longitudinal wave. And you can see here that you have this oscillating fluid element, and you can also see that there's a certain maximum distance that it's going to move in either direction. And you can see that there. That's why the S sub m, again, let me blow that up. So you can see the S sub m there and how that will it'll show you how far this particular oscillating fluid element will move in either direction. So, as the wave passes, an air element of thickness delta x oscillates left and right in simple harmonic motion about its equilibrium position. At the instant shown in B, the element happens to be displaced a distance s to the right of its equilibrium position, and its maximum displacement, again, is marked by S sub m. So, for displacement, a sound wave causes a longitudinal displacement S of mass element m in a medium, and is given very much like the formula that we've seen up to this point for simple harmonic motion. So S of m is going to be the displacement amplitude. In other words, this is the farthest it could go, but depending on what conditions, the time and other characteristics of the wave and where we are, it's going to be either at the maximum or perhaps some other place that is less than that. So we can see here, of course, k is equal to 2 pi divided by the wavelength, and omega is going to be equal to 2 pi f, the frequency. Pressure. So the sound wave also causes a pressure change, delta P of the medium, from the equilibrium pressure. And you can see the formula right there for the change in pressure. You're going to see that the pressure amplitude, the maximum, is going to be equal to the formula that you see there in front of you, which basically is built upon the displacement maximum times some other factors, velocity, density, and rho. Not rho, but omega. Okay, so interference. If you have 2 point sources, S1 and S2, and they're emitting spherical sound waves in phase, the rays L1 and L2 in that diagram are going to indicate that the waves pass through a common point P. The waves are represented with transverse waves. They're both going to arrive at point P. So remember, the waves are coming out in circles, and this L1 is going to be the ray that connects them. And then the same thing is happening here at S2, and they're going to both end up at this particular point P. So the interference at P depends upon the difference in the path lengths to reach P. Now, if we're looking at a situation of fully destructive interference where they're exactly out of phase, say 2.5 wavelengths, then you can see there the diagram on the left that that's how the transverse waves are going to look. They're going to be completely out of phase with each other. If, however, they are a wavelength different from each other, or multiples of that wavelength, then the waves arrive exactly in phase, and this is how things would look. In other words, you're going to see constructive interference where one is sort of assisting the other. And that is considered to be exactly in phase. So for the path length difference, the interference of 2 sound waves with identical wavelengths passing through a common point depend upon their phase difference at that point. If the sound waves were emitted in phase and are traveling in approximately the same direction, then we can say that their phase difference is going to be their path length difference divided by the wavelength times 2 pi. Fully constructive interference occurs when phi is going to be an integer and multiple of 2 pi, so you can see that. And equivalently, when delta L is related to the wavelength by basically your whole numbers here. This is going to be a fully constructive interference. Fully constructive interference occurs when phi, wait, did I see? Yeah. This occurs when phi is an odd multiple of pi, and equivalently when delta L is related to the wavelength by basically numbers that are greater than the whole numbers by 1/2. And you can see the fully destructive interference there. I think there may be a typo there. I think that should be destructive. Okay, intensity and sound level. The intensity of a sound wave at a surface is the average rate per unit area at which energy is transferred by the wave through or onto the surface. So the intensity is basically going to be your power divided by the area. So power is going to be the time rate of energy transfer, which of course is referred to as power, and then the area of the surface intercepting the sound. So the intensity I is related to the displacement amplitude of the sound wave by this particular formula. The intensity at a distance r from a point source that emits sound waves of power p sub s is equally in all directions isotropically with equal intensity is going to be given by this. So your intensity is going to be the power and divided by 4 pi r squared. So a power source S emits sound waves uniformly in all directions. The waves pass through an imaginary sphere of radius r that is centered at S. The decibel scale. So a sound level beta in decibels, and with a D in capital B, is going to be defined as beta is equal to 10 decibels times the log of the intensity divided by some standard intensity, which happens to be 10 to the minus 12 watts per meter squared. And that's going to be a reference intensity level to which all intensities are compared. That level is about the level where human hearing can start to detect sound. It's around that particular level. So for every factor of 10 increase in intensity, 10 decibels is added to the sound level. A sound is a very, very interesting concept because it can cause the wall of a drinking glass to oscillate. If the sound produces a standing wave of oscillations, and if the intensity of the sound is large enough, that glass will in fact shatter. So here are some examples of decibels. Rustle of leaves or whatnot. It's very quiet. It's about 10 decibels. Conversation, about the level I'm speaking right now, is about 60. Going to the rock concerts, about 110. You start hurting at about 120. And if you decide to listen to a jet engine, have fun with that. Now, sources of musical sound. So, standing sound wave patterns can be set up in pipes. In other words, resonance can be set up if sound of the proper wavelength is introduced into the pipe. So, let's say we've got a pipe here that's got 2 open ends on it. And if it has 2 open ends, what you're going to see here is that the open ends are going to be at the antinode of these particular waves as you see them come through. In other words, it's allowing for the maximum amount of flow at that point. So that's why it's defined this way. So if you look at that length L, you are able to gauge the wavelength. In other words, if you have a wave that looks like this, it creates one wavelength per length. So that's its wavelength. If you start looking at this particular formula here, you can see the frequency is going to be equal to the velocity of the wave divided by the wavelength. One easier way for me to remember this is that if you take the wavelength over here, the wavelength times the frequency should always equal the speed. So this pipe open at both ends will resonate at these frequencies. So if n is equal to 1, 2, 3, or 4, this is how you will see the resonance of the pipe. If, however, one of these is closed, what you're going to end up seeing is that you're going to have a node at the closed end of the pipe. How the wave behaves after that, it could be here. Again, this is going to be a length of L. So if you have it going from the node up to one of the antinodes here, that's about a quarter of the wavelength. If you manage to get in one more part of a wavelength here, you can get 4L divided by 3, 4L, and if you can even add in another one, 4L divided by 5, 4L divided by 7. That open end always has to be an antinode. So however you're getting these waves in here, this is how it is increasing. So you've got only odd harmonics that can come out of this. That's why this is set to 1, 3, 5, because this condition has to be a node, that has to be an antinode. And so the wavelengths that are coming about is I can start with a half, and then I can add in another, or you start with a quarter, and then you can add in another half, and then another half on top of that, so on and so forth. So that's how this really comes about. Now, beats, if you've ever listened to instruments trying to tune in a band, or maybe you've seen an orchestra or something like that, beats will start to arise whenever two waves have slightly different frequencies. And if you've got two different frequencies, F1 and F2, and they're, you can hear them both, then the beat frequency is going to be the difference between those two. So let's say you've got A and B. These are two different frequencies. If you were to superimpose those, this is the kind of frequency you're going to end up hearing. So the pressure variations, delta P, of the two sound waves, as they would be detected separately, is what you're seeing here. The frequencies of the waves they're very close, but as you would expect out of an orchestra or a band, you want them to get to be exactly the same frequency. But if they're not, you're going to hear a difference in the resultant pressure variation if the two frequencies are detected simultaneously. In other words, if you take the difference between the two, this is what it's going to end up looking like. So, the Doppler effect. The Doppler effect is going to be a change in the observed frequency of a wave when the source or the detector move relative to the transmitting medium, such as air. So for sound, the observed frequency, F prime, is given in terms of the source frequency F by this formula. This is going to be the Doppler effect. In other words, the frequency is going to change, and it's going to change by multiples of whether or not the source is moving or whether or not what's detecting it is moving. And this is the formula to use in order to be able to do that. So you can see here v is going to be the speed of sound through the air, and then vd is going to be the detector speed relative to the air, and this is going to be the source of speed relative to the air. Remember back when we were discussing in one of the previous chapters, I think it was chapter 4, chapter 5, where things are relative, the speeds are relative to each other. Well, this is another instance in which we have to take that into consideration. So in the numerator, the plus sign applies when the detector moves towards the source, and the minus sign applies when the detector moves away from the source. When you're increasing the distance, then the frequency is going to fall. When you're walking towards each other, or one is walking towards each other, or both are doing it, then you're going to see an increase. In the denominator, the minus sign is used when the source moves towards the detector. The plus sign applies when the source moves away from the detector. The denominator basically works the opposite direction, because if you want to make sure that you've got this calibrated right, if you were to drive closer to an ambulance, you should hear the frequency of that pitch, of sound that the ambulance makes. You should hear that be higher. As soon as you pass it, it will drop. So the way you do that is to, if you're moving towards each other, is to add them in the numerator and then subtract them in the denominator. And then whenever you two pass each other, then as the frequency drops, then that number that's being multiplied should end up decreasing. That's why it works the opposite direction. So we've got a detector moving towards a stationary source. So you've got this magic ear here. Think Harry Potter or whatever you would like. And it is moving towards the source. As it moves towards the source, then the shift in that frequency should get, the frequency should be higher. If you have a source moving towards a stationary detector, what you're kind of seeing is that the sound waves kind of bunch up a little bit as the progress is being made. And so therefore the frequency of this should increase. Now, if the speed of a source relative to the medium exceeds the speed of sound in the medium, then the Doppler equation no longer applies. In such a case, a shock wave is going to result. And if you've ever seen some pictures of the sound waves that are generated by something that's flying supersonic, those are some pretty cool things to behold. The half angle, theta, of the Mach cone is going to be given by this particular equation. So you've got something that's traveling this fast. So a source moves at a certain speed, faster than the speed of sound, and thus faster than the wave fronts. So when the source was at position S of 1, it generated wavefront W1, and at position 6, it's generating W6. All these spherical wavefronts expand at the speed of sound and bunch along the surface of the cone called the Mach cone, forming a shock wave. And the surface of the cone has a half angle, theta. In other words, the full angle here is one thing, but that half angle there is going to be referred to as theta and is tangent to all of the wavefronts. Okay, waves can be some pretty cool things, and I think as you go through the material in the book, I think you'll find some of the examples are pretty interesting.